Here we present VisuoSpatial Foresight, an algorithm for learning a goal-conditioned fabric manipulation policy. Fabric manipulation has applications ranging from laundry folding and bed making, shown here, to manufacturing upholstery and handling surgical gauze. However, robotic manipulation of deformable objects is very challenging due to the infinite dimensional state space and complex dynamics. The difficulty in modeling fabric motivates the data-driven strategies explored in recent work, but existing work in robot fabric manipulation is limited to and often highly engineered for a particular task, such as fabric smoothing or folding. In this work, we seek to lift this limitation by learning a general-purpose fabric manipulation policy that can take actions towards some desired configuration provided as a single goal image. To do this, we decouple dynamics from planning by learning a video prediction model and reusing it across different fabric manipulation tasks. This framework was introduced in prior work as Visual Foresight, which we extend to VisuoSpatial Foresight, or VSF, with the addition of depth maps, which we find to be beneficial in our experiments. We use an open-source fabric simulator to efficiently and safely generate enough data for training the model. This data consists entirely of random actions taken on the fabric without any demonstrations of specific tasks. The first step in VSF is to train a visuospatial dynamics model. We learn a mapping from an image observation and an action sequence to the resulting sequence of images, where our actions are specified as pick points and pull vectors in the XY plane. Here we show two trajectories predicted by our model at test time, given the single context image on the left and a sequence of 4 actions. We compare against the ground truth trajectories generated by these actions and hypothesize that our predictions are sufficiently accurate for planning. We apply domain randomization to fabric color, brightness, background plane shading, and camera pose to facilitate sim-to-real transfer. We proceed to plan over our learned dynamics model with model predictive control. Given an arbitrary goal image, at each time step we use the cross-entropy method to approximate the action sequence that gets us closest to the goal under the Euclidean distance metric in pixel space. Here we show 3 example trajectories during planning given the initial observation in the top left and the fully smoothed goal image in the top right, where we plan over a horizon length of 5 images and proposed actions are projected onto the images as arrows. We first evaluate our policy on the fabric smoothing task, in which we wish to maximize coverage of the underlying plane. To do this, we pass an RGBD goal image of a fully smoothed fabric to the trained VSF policy. We compare against several analytic baselines as well as an imitation learning agent trained specifically for smoothing using Dagger. We find that despite seeing 0 smoothing demonstrations at training time and not explicitly optimizing for coverage, we are able to significantly outperform all analytic baselines and match the performance of the imitation learning agent across 3 different tiers of difficulty. Here we show an example rollout of VSF on the smoothing task in simulation as a time-lapse of observations taken after applying actions and letting the fabric settle. For clarity, we only show the RGB channels. These are the actual 56 by 56 observations given to the model, which are downsampled due to the high computational complexity of Visual Foresight. We next apply the same VSF policy, but this time with an initially smooth configuration and a goal image of a diagonally folded fabric. Here we show an example rollout, where the underside of the fabric is a darker color. We attain 90% reliability on the folding task and find that leveraging depth in addition to color yields an 80% improvement in performance. We then provide a goal image of a doubly folded fabric with 3 layers stacked in the center of the fabric. While we attain lower reliability, VSF is able to doubly fold fabric as well. Finally, we transfer the VSF policy to a real DaVinci ResearchKit surgical robot. Here we show a successful smoothing episode with a highly crumpled initial state. We compare against the imitation learning baseline and find that we can rival its performance in a physical setting as well, despite the no-ops caused by occasional near misses. In conclusion, we present an algorithm and system toward general robotic fabric manipulation. While VSF yields a more general policy than imitation learning, it does take about 30 times more computation time during execution, as we must make thousands of forward passes through a large neural network as opposed to a single pass. In addition, compounding approximations in the physics simulation, visual dynamics model, and a relatively simple cost function become apparent when attempting more difficult tasks on the physical system, such as folding. In future work, we hope to augment the action space, increase the task set, and improve reliability. Thank you for watching. Please see the project website for supplemental material, including open source code and the paper appendix.